Hello, assalamu alaikum everybody. How are you doing? Well, today I am going to start talking about a new chapter, and as usual at the beginning I give you a motivation about the general ideas of this chapter. Then after that we get into the technical details of what we need. So far we talked about vector spaces and linear transformations on vector spaces and so on and so forth. But when you think about a vector space here, think about you are discovering a new planet and you want to go and live in that planet. Well, once I remember I asked my students, suppose we discovered a new planet and you want to go and live in that planet, what do you need? And one student said, we need water, we need food, and we need a partner. Well, I agree, we need water, we need food, but I'm not sure about the third one. So you can think here about the water and the food as your vectors in the vector space. But for us, as mathematicians or as scientists in general, we want a way to measure things. So when you are in a new planet, you need to develop a way to measure things. How to measure distance, how to measure weight, how to measure time, how to measure age, and so on and so forth. Okay, so it's natural here to start thinking about, okay, I have a vector space and I'm living in that vector space, so how can I measure the distance between two vectors? How can I measure the length of a vector? Well, that is something we need to address now. Of course, when we try to develop something, we do not come like with strange, weird ideas. Our ideas, they develop from the things that we know. They develop from natural things. Okay? And I always say, it is like if you think about mobile devices. Like 20 years ago, mobile devices, I mean, like if you talk about mobile phones, they were like this big and they don't have a lot of fancy things. They were just very simple. Then we start to develop that. Well, here, when you have a vector space, we need to think about how do we measure things there. And in that case, we need to define what we call an inner product. So I start here by definition. An inner product, on V is a function from V cross V to the real numbers. That will do the following, okay? Or that satisfies certain conditions. But because we want here to make it kind of well-defined way of doing things, okay? So we need here certain conditions to be satisfied. Number one, my function here, your book is using this for your function. So this here in V, this vector in V. So what we need here, we need the first thing is UV to be the same as VU. So this is 1. So if you measure things between U and V, it's the same as if you do it between V and U. Okay? Number 2. We need KUV to be KUV for any K belongs to R. And of course, any UV in your vector space V. Number 3, we need U1 plus U2 V to be the same as U1V plus U2V. Number 4, we need inner product between U and U to be larger than or equal to 0. And U, inner product U, is 0 if and only if U is the 0 vector of V. Okay? So those 4 conditions must be satisfied to say that you have an inner product in your vector space. Now, you will see in a minute why do we need these conditions to be satisfied. Suppose I have defined something that will satisfy 1, 2, 3, 4. In this case, we can define 1, the length of a vector. The length of a vector, U, look, we are using this for the length, okay? The length of a vector U. So this is like in your school math when you talk about the absolute value, okay? So when you talk about here, X belongs to R, and you talk about absolute value of X, what do you mean by that? You mean by that here, the distance between your X and, or if your X is here, so this will be the distance between X and 0, or the length of X. So here we use the norm, okay? But if you don't like this, you can say the length of U. What is the length of U here? The length of U, well, look here. Inner product UU, we wanted this to be larger than or equal to 0. So now we can say here this is the square root of U inner product U. So we define the length to be the square root of the inner product between U and U. Number 2, the distance. The distance between U and V, we call it DUV. All right. Suppose, let me go back here to the real numbers because that is easy for you to see here. Suppose I take the real numbers here and I tell you this is my X and this is my Y. And I ask you what is the distance between X and Y. What's the distance between X and Y? Well, you can say it is Y minus X, correct? Well, in general, if you don't know which one is to the left and which one is to the right, you can say this is absolute value of Y minus X. So absolute value of Y minus X, it will give you the distance between X and Y. Okay, I'm making it simple here. I'm talking about the real line. Similarly here, if I'm talking about the distance between U and V, that will be the norm of U minus V. So the norm here will do the job of the absolute value here, and in that case we can talk, sorry, this is V. U minus V norm. So now, if you define something that will satisfy those 4 conditions, then you can talk about length and you can talk about distance. And that is what I'm going to do today. Later on, we are going to talk about more things that we can get from an inner product space. Like we can talk about the angle between vectors, we can talk about orthogonality, we can talk about many things when you have an inner product. Well, I'm going to give you some examples. But before I give you some examples, let me here write a remark, and that is very important remark. Whenever you have a vector space, you need to ask yourself several questions. Number one, for a vector space, the first thing you need to ask yourself, don't wait for a professor to ask you this question. Ask yourself the question, what is the dimension? What is the dimension? 2, ask yourself, can I find a basis? Number 3, can I define an inner product can I define an inner product on my vector space? So for each one of the vector spaces that we have seen, you need to think about those questions. And don't wait for a professor to ask you about that. You need to do that. Maybe it's good to put them in a table and summarize or give answers to those questions for each vector space we've seen. For example, when you have Rn, when you have Pn, when you have M by N, or M by N. Okay. What other vector spaces we talked about? We talked about a couple of more examples. It doesn't matter which vector space you have. You need to think about each one of those questions. All right. So now let me go back and give some examples. Example number 1, and again I'm going to start by a very easy example. Example number 1. My vector space is R3. I want to define my inner product to be the following. Define my inner product as follows. Well, take it from something you already know here. Well, you know from your physics the dot product, correct? So when you have two vectors, U equals, let's say, x1, x2, x3, and V equals y1, y2, y3. So how did you define the inner product between them? Or you can say this is x1i plus x2j plus x3k. And this you can say y1i plus y2j plus y3k. So this is your u, this is your v. So u dot product v. Maybe in your physics courses you talked about only vectors in R2. But whether it is R2 or R3, it is the same. So U dot V, what was that? It was X1, Y1 plus X2, Y2 plus X3, Y3. Well, that is exactly what we are talking about here. So here, I am going to take my inner product to be the dot product that you know from your general physics 1 or 2. So here, I want to define. So here this is just relating what I'm doing here with something you already know. Okay, so define here U, V to be this. X1, Y1 plus X2, Y2 plus x3, y3. All those three conditions are satisfied by default. If you do it in this way, all of them are satisfied. Well, let's check them one by one. This is an inner product on R3. Well, number one. Look, some of them, they are very easy. You see that right away, so I don't need to write much here. Look, U, V, V, U. If you do it, U, V, you get this. If you do VU, what do you get? You get Y1, X1, Y2, X2, Y3, X3. So that is very obvious in this case. UV and VU are the same. You see it from here. Okay? Number two. What happens if you multiply U by scalar K? Well, from here, it means you are multiplying the components of U by K. So Kx1, Kx2, Kx3. So what do you get here? You get Kx1, Y1 plus Kx2, Y2 plus Kx3, Y3. Now, take K as a common factor. So this will be K into X1, Y1 plus X2, Y2 plus X3, Y3, and that is going to be K into U, V inner product. So the second condition is also satisfied easily. Okay, what about the third one? The third one, you have U, you have V, so we need a third vector here. Let's take W to be Z1, Z2, Z3. So U plus W, V. What is that? U plus W, it means X1 plus Z1 multiplied by Y1 plus X2 plus Z2 multiplied by Y2 plus X3 plus Z3 multiplied by Y3. Now, unfold this. What do you get? You get X1, Y1. From here, you get X2, Y2, X3, Y3. And from here, you get Z1, Y1, Z2, Y2, Z3, Y3. Put those together, what do you get? You get U, V plus W, V. And that is the third condition here. Okay? So the third condition here is also satisfied. What about the fourth condition? Well, the fourth condition is very easy to see. Look, U, U. So when you do here U, U, what do you get? You get X1, X1, that is X1 squared. You get here X2 squared, and here you get X3 squared. Correct? Something squared, something squared, something squared, you add them, what do you get? For sure you get something larger than or equal to 0. More than that, let me clarify this here. So, when you have U, you are going to get X1 squared plus X2 squared plus X3 squared. That is larger than or equal to 0. And when you take U equals 0, you get what? You get X1 squared plus X2 squared plus X3 squared equal to 0. And when do you get this 0? You get this 0 when X1 equals X2 equals X3 equals 0. And that means U equals the 0 vector. Okay? So the four conditions here, they are satisfied easily. I'm talking about R3. What if you talk about R2? What if you talk about R4? What if you talk about Rn? If you talk about Rn, then it is the same thing. Okay? So here, what you do, you multiply component-wise. Okay? So you can define an inner product just by multiplying component-wise. This inner product, actually we are using it from our early math days, and that is called the Euclidean inner product. The Euclidean inner product. Okay? So whenever you talk about Rn, right away you can define easily an inner product. It is the Euclidean inner product. Okay? All right. So I'm not going to spend too much time on this because it is what you already know. Okay? So if I ask you what is the distance between two vectors or 2 points in the plane, you can use this and find the distance, which is exactly the distance that you know from your elementary school. Okay? Let's make this more interesting. So here is example 2. I'm going to take my vector space to be R, again, R3. So your U is x1 as before, x2, x3, and your V is y1, y2, y3. I'm going to define my inner product, UV. By the way, your book is using this sign for the inner product, but if you don't like it, you want to change it to something else, it's fine. However, we have to be consistent, okay? So what is this? This, I'm going to make it 2x1, y1, plus 3x2, y2, plus x3, y3. So I'm changing this. This is not the inner product or the dot product that you had in your elementary physics courses. Okay? Well, are we going to get the 4 conditions satisfied? Well, since I clarified this here, it is easy now to clarify them here without going through the details. Look, UV. What happens if I put VU? You are going to swap those, you get the same thing. So the first one here is satisfied. What about the second one? If I multiply U by K, so it means K here, K here, K here. It means K here, K here, K here. Take it out as we did here. So this is satisfied. What about this one? Well, as we did here. The only difference here, you are multiplying here by 2, here by 3, and this is the same. Okay? However, the same steps. Okay? So 3 is satisfied. What about 4? 4 here. U with itself, what do you get? You get 2x1 squared, 3x2 squared, and here you get x3 squared. So as we did here, but you are going to have here 2 and here 3. Correct? So you get the same thing. And that is the same. Okay? So basically, all 4 conditions are satisfied if you do this. Now, since here we are giving this some weight, so we can say this is the weighted inner product. Because it's similar to this inner product, it is just we are giving weight to each component or each term here. Okay? So this is again an inner product. It is an inner product. So I left some steps here. Please write the steps because for you, you need to practice how to verify those 4 conditions. Okay? So this is an inner product. It is called the weighted Euclidean inner product. This is the Euclidean inner product. This is the weighted Euclidean inner product. Okay? Now, since I'm talking about those, let me here clarify a few more things. Those I like to keep here in front of you, or maybe this also I should keep it. This, let me also keep it and move here. In this vector space together with this inner product, what is the distance? Or what is the length? What is the length of this vector? V equals, let's say, 1, -1, 0. What is the length of this vector? Look, if you do it using the previous example, using the inner product or the Euclidean inner product, you are going to get 1 squared plus -1 squared plus 0 squared. That is the length of your V, which is going, under the root, which is square root of 2. So this is the length under the Euclidean inner product. What happens if we do it under the weighted inner product? We are going to get length of V equals square root of V together with V, and that is going to be square root of 2 times 1 plus 3 times 1 times minus 1 or -1, -1. So this is -1, -1. So what do you get here? You get 2 plus 3, 5, square root of 5. Okay? So under this inner product, we got the length of V is square root of 5. Under the Euclidean inner product, we got the length of V square root of 2. And maybe here you are thinking, oh, Professor, how can I get 2 different lengths for the same vector? Well, when you define an inner product, it will give you a new way of measuring things. Well, let me give you an example. If you ask me about how tall are you, I will tell you I am 176 centimeters. This is how tall I am. Well, if you ask me the same question in the United States, I will tell you I am 5'10", like this. So, what are we talking about here? Am I giving you different? Well, approximately. Approximately. Am I giving you here different answers? No, I'm giving you here approximately same answer. It is just here I am using centimeters and here I am using feet, inches. Okay, why? Because in the States they are using the feet, inches system. Here we are using the meters, centimeters system. Okay, so here you think about different inner products on the same vector space as different way of measuring things, like measuring in kilograms or measuring in pounds, like measuring in centimeters or measuring in inches. Okay, so don't be surprised here. Similarly, if I talk about, for example, the unit circle or the unit sphere, the unit, let me make it here unit circle, so all of you are familiar with that. The unit circle. Well, what is the unit circle here? It's a circle of radius 1, correct? So in the plane, how do you use to do that? So you say here is the origin, and here is a circle of radius 1. Correct? So what do you mean by that? You mean that by that all points in the xy plane that are 1 unit far from the origin. So how do you represent that? That is going to be x squared plus y squared equals 1. Correct? Isn't that the equation of the circle, of the unit circle, you know, from your school math? Why do you say this? Because here you are using the Euclidean inner product. Okay? Now, if I tell you what is the unit circle under this weighted inner product, then don't tell me this. You have to answer the question in a different way. You have to say, okay, that means all vectors in the plane, all vectors in the plane such that the length of U is 1. Now, the length of U is going to be affected by the inner product that you are using. Okay? So here, if you are using the inner product, the weighted inner product, you are going to get here your unit circle different from, the graph different from this one. Let's see why or how. Let me take here inner product, my inner product, UV to be 2x1y1 plus 3x2y2. I'm talking about R2 here, so I'm going to take this. So here, length of U is going to be square root of 2 x1 plus 3x2 squared. And I want this to be 1. So what are we getting here? We are getting 2x1 squared plus 3x2 squared equals 1. So if you go back here, it is not going to be this. It is going to be this. 2x squared plus 3y squared equals 1. So based on this inner product, your unit circle is going to be all points that satisfy this equation. Well, what is this equation? Certainly this is not a circle. This is going to be an ellipse. I'm not going to focus on the details, but this is going to be an ellipse. Okay? So when we say a unit circle, we say a unit circle under the inner product that you are using, okay? But don't keep in your mind that is going to be exactly rounded, the rounded circle that you know from your school math, okay? It will be that circle if you are talking about the Euclidean inner product. If you change that into a different inner product, the shape could change, okay? But however, the equation is the same, okay? All right, so now in this example, we talked about the length and we talked about also the distance. It's the distance between your points and the origin, correct? All right, let's take another example. So far, we are talking about Rn. Let's take a different vector space. This is example 3. My vector space V equals P2. Polynomials of degree at most 2. So this is my vector space. Do you know an inner product in this? So far, no. Let's define this inner product. Define as follows. Take two polynomials and define the inner product between them as, okay, let me write here what do I mean by Px. It's a polynomial in P2, so this has to be A1x squared plus B1x plus C1. Am I correct? Qx is A2 x squared plus B2x plus C2. So this is my general P, this is my general Q, and now I want to define the inner product between them as A1, A2 plus B1 plus B2 plus C1 plus C2. Now maybe you're saying, Professor, how did you come up with this formula? Well, when you define this, you have to keep in your mind that the four conditions have to be satisfied. Okay? So when I give this, in my mind, I want these four conditions to be satisfied. So after some practice, you are going to figure this out. So from the beginning, you can realize whether your conditions are going to be satisfied or not. Or at least, you have a feeling about it, whether it is satisfied, whether they are satisfied or not. Okay? So, 1, if you take P, Q, this is the same as QP. Do I need to write something here or is it clear? P, Q, QP, what happens? So let me write it. A1, A2 plus B1, B2 plus C1, C2. That is going to be the same as if I write A2, A1 plus B2, B1 plus C2, C1. Now, what is this? This is going to be QP inner product. So PQ inner product is the same as QP inner product. Okay, according to this definition. Number 2. What happens if I multiply P by K? Well, it means K, A1, A2 plus B plus K, B1, B2 plus K, C1, C2. Again, take this K out and you get K inner product PQ. All right, 3. P1 plus P2 Q. What is that? So in this case, I need here, or instead of saying, let me keep P, and here keep, or write this as P, Q, and L. And my L, I'm going to take it as here L of x to be A3 x squared plus B3x plus C3. So what is this going to be? This is going to be A1 plus A3 multiplied by A2 plus B1 plus B3 multiplied by B2 plus C1 plus C3 multiplied by C2. And now unfold this and put things together. So this is A1, A2 plus B1, B2 plus C1, C2 plus A2 or A3, A2 plus B3, B2 plus C3, C2. So this here and this here will give you what you want. Will give you P, Q, and this will give you here L, Q. So the third condition is also satisfied. What about the fourth condition? U larger than or equal to 0. Well, let's do that. I think now you remember those, so let me erase this part. Or take P of x with P of x. What do you get? you get A1, this is A1 squared plus A plus B1 squared plus C1 squared. Obviously, this is greater than or equal to 0, and this is 0 if and only if Px is 0. So the fourth condition is also satisfied. Okay? So from now on, when you talk about polynomials of degree, not necessarily 2, you can now talk about polynomials of degree 3. It's in the same way. You can generalize this. So even if it's polynomials of degree n, you keep doing this in the same way. Okay? So when you have, in general, when you have Pn, then inner product Px Qx will be A1 A2, B1 B2, C1 C2 plus D1 D2 plus and so on and so forth. Okay? Let's now talk about the length. Question, find the length of this polynomial, y equals x squared minus 1. What is the length of this polynomial? What does that mean? I mean, if you think about your school math or your pre-calculus, this question doesn't make sense, correct? What is this? This is this polynomial or this function. Negative 1, and here 1, and here negative 1. Am I correct? So this is y equals x squared minus 1. So what does it mean, find the length of this polynomial? Are you asking you about the length of the curve? No. Are we asking you about the length of certain points or how far certain points are going to be from the origin? No. We are asking you about the length of this polynomial with respect to this inner product. So how do you do that? Here is how you do it. Length of x squared minus 1 is square root of x squared minus 1, x squared minus 1 inner product. This will give you a well-defined quantity. That is what we call the length of this polynomial under this inner product. So what is that? This is going to be square root of, okay, let's apply this, A1, A2. So that is going to be 1, 1 plus negative 1, negative 1. Well, the middle term you get 0 here, and here negative 1, negative 1, so this is square root of 2. So the length of this polynomial is square root of 2. Okay? All right. What about if I ask you this question? Find the distance between y equals y1 equals x squared minus 1 and y equals x. What is the distance between those two polynomials? Please don't graph them and tell me, yeah, this is y equals x squared minus 1 and here is y equals x. And then start to think, oh, what is the distance between them? Is it, well, here they intersect. What does it mean, the distance between them? Here they are, the distance between them can be measured. But what does it mean, the distance between them? Don't think about it in that way, okay? The distance between them is going to be distance between y1 and y2 is going to be the length of y1 minus y2. Okay? And how do you do the length? You do it as we did it here. Okay? So that is going to be distance y1, y2 equals square root of what? y1 minus y2, and here y1 minus y2. Now what is that? Square root of y1 minus y2. So this is x squared minus x minus 1, and here x squared minus x minus 1. Am I correct? Now this is going to be what? This is going to be 1, 1, 1. So that is 1 plus 1 plus 1, and that is the square root of 3. So the distance between this polynomial and this polynomial is square root of 3. Okay? So don't think about it in the same way as you used to think in your school math. Think about it in terms of the inner product that you have and in terms of the distance formula that you get from that inner product. Okay? All right, so we have an inner product over Rn. We have an inner product over Pn. Well, here I give it over P2, but again, generalize this over Pn. It seems all the examples I gave you are inner products. Well, let's take another example. And here, I'm not going to think about it. I'm going to just throw something. Example, that's number 4. On or in this vector space, V equals R3, define U, V as, so my U is as before, x1, x2, x3, and my V, y1, y2, y3. And now I want to define x1, x2, plus 2x, no, y1 here, x1, y1, plus 2, x2, y2, minus 4x3, y3. Is this an inner product? Is this an inner product? That's the question. Is this an inner product? Well, you need to check here the 4 conditions. Okay? However, you can here get a hint. Look, you have a negative here. And this negative, it's going to screw up the 4th condition. Correct? So all you need here is to think about the 4th condition, which is, so here, no, because if you take u, what do you get? You get x1 squared plus 2x2 squared minus 4x3 squared. Now, is this larger than or equal to 0 all the time? Well, not necessarily. This could make it negative. So, for example, if your u is, let's say here 1, here 0, and here 1, then u is going to be 1 plus 0 minus 4, 1 plus 0 minus 4, and that is negative 3. It is not positive or 0. It's negative. So this condition, number 4, is not satisfied, because condition 4 is not satisfied, because condition 4 is not satisfied. Okay? So condition 4 here is not valid, so this is not an inner product. Okay? All right. One more example here. So we talked about an inner product in Rn and inner product in Pn. Let's talk about an inner product on example number 5, 3, 4, 5. This is 5, I think. Okay. Let your vector space be, let's take it all 2 by 2 matrices. Once you understand the example, then you can ask yourself, what about 3 by 3? What about n by n matrices? You can generalize that. So this is our vector space. And A, B are 2 matrices NV. Define A, B inner product to be this. Trace A transpose B. Look, those are 2 vectors in this vector space. The trace of the product here, that is going to be a real number. So I'm defining here a function. So what is this? This is a function from V cross V into the real numbers, because the input is coming from here and the output is going to be here. Now, is this an inner product? Is this an inner product? So look here, I put dot dot when I talk about that in general, okay? So here I'm giving the formula for specific A or for A and B, but here I'm talking about it in general. So is this an inner product? Well, we need to check the 4 conditions. Now, in case you don't see this, or you don't understand this, you can try here to take specific matrix or specific matrices and unfold this and try to understand it better. So let's do it here like in the margin. Let's try to understand it better. What is trace A transpose B? So let's say here your A is this matrix. A1, B1, C1, D1. And your matrix B is A2, B2, C2, D2. What is trace A transpose B? This is going to be A1, B1, C1, D1, and that is going to be B. So A2, B2, C2, D2, and you have the trace of that. So I should have left some space here. So the trace of this. Now, when you multiply, what do you get? You get the trace will be A1, A2, this by this. Well, let me write it here. That is a trace of A1, A2 plus C1, C2. And here this is I don't care about it. This I don't care about it. This will be B1, B2, and here plus D1, D2. So the trace will be A1, A2 plus C1, C2 plus B1, B2 plus D1, D2. So now if you compare it with A and B here, what are you doing? A1, A2, B1, B2, C1, C2, D1, D2. So you are multiplying component-wise. So basically that is going to be similar to the standard inner product or the Euclidean inner product over Rn. It's the same idea, just we are multiplying here component-wise. Okay? So now this here, it should not bother you. Okay? You know what we are talking about. When we talk about this, it is like we are telling you multiply component-wise. Okay? Now, show that this is indeed an inner product. Well, you need to check the 4 conditions. And I do not recommend that you do it in this way, because this is just in the margin to help you understand what's going on, okay? Because if you want to prove the conditions using this, it's too much writing for nothing, okay? So we can do it in a smart way using the same formula that we have here. So let's do it. Yes, because 1, inner product AB is going to be trace A transpose B. And here at the end, I want this to be BA. So how can I go from here to here? Well, let's go back from here, one step back. So what is this? This is a trace B transpose A. Now, how can I go back from this to this or forward from this to this? Okay, so let's see here. This, you know from the properties of the trace and the transpose, this is the same as trace B, A, transpose, all transpose. Maybe I should leave some space here. The trace of a matrix is the same as the trace of the transpose of that matrix. So here, this, this should be here. Okay, yes. Now, this is going to be trace of B transpose A. Trace of this transpose is the same as trace of this. And that is going to be exactly inner product B A. Okay, so the first condition here is satisfied. The second condition. What about K, A, B? This is going to be trace K, A transpose B. And this is trace K, A transpose B. And this is what? Well, you know what happens to the trace when you multiply your matrix by constant, correct? That does not affect the trace. You take it out. K trace A transpose B. Three. A1 plus A2 and here B. What is this? Well, that is going to be trace of A1 plus A2 transpose multiplied by B. And now, use the properties of the transpose and the trace. What do you get? You get A1 transpose plus A2 transpose and here B. Now, multiply, you get a trace of A1 transpose B plus A2 transpose B. Now, again here, the trace of the sum is the sum of the trace, correct? Do you remember that from chapter 2? From chapter 2? That is trace A1 transpose B plus trace A2 transpose B. And now, that is exactly what you want. So here, that is A1B inner product plus A2B inner product. The last one, number 4. What happens if you take A with itself? What do you get? You get a trace of A transpose A. Correct? Now, think about you are multiplying a matrix by its transpose. Correct? So think about when you multiply. Then you take the trace. What do you get? You get the elements along the diagonal squared, correct? So that is going to be A11. I'm talking about 2 by 2. So here A11 squared plus A22 squared plus A. That's it. It's 2 by 2 here. But even if it is in general, 3 by 3, 4 by 4, n by n, it's the same idea. Okay? So this is 2 by 2, and that is larger than or equal to 0. And right away you see if this is 0, it means this is 0, this is 0. And in that case, no, I'm sorry. Trace A transpose A. What is that? That is going to be A11 multiplied by A11 plus A2 multiplied by A2 plus A12 multiplied plus A12 multiplied by A12, which is A12 squared, plus A21 multiplied by A21, which is A2 squared. So you can see it from here if that's not clear to you. When you multiply here, and you get the trace, so what do you get? You get A1 and here A1, you get C1, C1, you get B1, B1, you get D1, D1. So that is going to be this, and this is larger than or equal to 0. Now, when this is 0, it means each one of those guys here has to be 0. So here Aij has to be 0 for I equals 1, 2, J equals 1, 2. And that means your A is the 0 matrix. Okay? So here I did it using the properties of the trace and the transpose. Okay? Again, please don't do or don't check those conditions using this. It will be too much work for nothing. Do it in this way. Now ask yourself the same question. What if you take this 3 by 3. Okay? Do it as an exercise, please. Take your V to be 3 by 3, define your inner product in this way, and check the 4 conditions. Okay? All right. Let me here ask you about, let's say here, the length of a matrix. Since we have the matrix in front, the inner product in front of us, we can talk about the length and the distance. Question, find the length of this matrix. 1, -1, 0, 1. What is the length of this matrix? Well, according to the definition, this is going to be square root of this inner product itself. So here it is. Inner product 1, -1, 0, 1 with itself. 1, -1, 0, 1. And what is that going to be? That is going to be trace of this transpose multiplied by this, and that is going to be, if we skip here that step, it will be 1 into 1 plus -1 into -1 plus 0 into 0 plus 1 into 1. And that is under the radical, and here what do you get? 1, 2, 3, square root of 3. So the length of this matrix is square root of 3. Okay, and now I can ask you, what's the distance? What is the distance between A equals 1, -1, 0, 1, and B equals 1, 1, 0, -1. What's the distance between those two matrices? Don't tell me the distance, you measure this distance. No, the distance here is the distance we got from the inner product, which is distance between A, B is length of A minus B. And that is going to be length of What is a minus b? That is 0. That is negative 1. This is negative 1. And this is 2. And what is the length of this? That is the square root of 0 plus 1 plus 1 plus 4. So that is the square root of 6. So the distance between those two matrices is square root of 6. Okay? So here I gave you several inner products. All of them, it's like the standard, simple inner products. I can give you more sophisticated inner products, but why don't you do here some exercises, and over the exercises you are going to find different types of inner products. For example, if I give you here the vector space of continuous functions over the interval AB. This is not finite dimensional. This is infinite dimensional vector space. Okay, I did not talk too much about it. But if we take this vector space, you can define here the inner product to be integral from A to B, f of x, gx, dx. That is kind of very interesting here. You use the integral to define an inner product on this vector space. Okay? Well, if you want to check the conditions, they are very easy to check here. They follow from the properties of the definite integral, which is something you know from calculus 1. Okay? So it will be an exercise here. Check the 4 conditions, and after that, ask yourself, can I find the length of a function? Can I find the distance between two functions? So I'll leave it for you as an exercise. And by this, I'll finish this section. All right, so thank you very much. And please do some exercises, practice some exercises here, okay? All right, bye-bye.